Hello, everyone. This is Mr. Smith. Thanks for coming back to talk about chemistry, specifically chemical reactions, specifically double replacement reactions. We're going to be able to look at those products today and figure out if a reaction happens at all. So, a double replacement happens in an example like this you see on the screen, where we have two aqueous ionic compounds mixing together. And then we see kind of a couple of things, indications of a chemical reaction. We see a color change going from colorless to yellow, and we see a cloudy puff of dust form, which is actually a solid, a really fine powder solid that disperses in the liquid. And so we have two ionic compounds coming in, two ionic compounds coming out. Cations mix up with the other anions. So here's lead finding the chromates, and here's the potassium finding the nitrates. And you get properly crisscross products again. That's balanced to make sure that the conservation of mass is satisfied. So some pretty cool kind of surprise reactions happen with the double replacements. It looks like a whole lot of nothing, and then something happens pretty fast. So here's our double replacement slide. Again, here's your generic letters, and here's a couple of examples here. We can actually make solids this way, we can make gases this way, we can make liquids this way, and we can make aqueous. So really the four phases. I know plasma is always the fourth phase, but as chemists working with chemical reactions, we don't deal with plasma too much. We deal with solids, liquids, gases, and aqueous. So a couple aqueous things goes into it. Whatever the color are, the end product could have a change of color and certainly a change of states. And so again, we have two ionics coming in, two ionics coming out. Water is always kind of thrown in there as an exception. You can have water be a reactant, you could have water be a product. Again, water is always an exception and always kind of finds its way into most situations here. Okay. And so as we can mix things together, what we're going to work on today is not predicting the products, but actually predicting the physical states. When is it a solid? When is it an aqueous? When is it aqueous? When is it a liquid? When is it a gas? And so there's a few rules to do it. Now, in here in our course, we're not going to deal with any of the gases. That's why I took the gases off of this slide. But we are going to be able to determine solid, aqueous, and liquid. And so when we do chemical reactions, we try to have all this kind of information in detail. And you've seen these kind of throughout the year, but now it's kind of put together on one slide for you. Plus means multiple reactants or multiple products. An arrow separates a reactant from the product. The double arrow we're going to use later in the year. And then the physical stage. And this is what we're going to work on today. Solid, liquid, gas, and aqueous. And then down here, if you put something on top of the arrow, that's a catalyst. Something kind of, it's not a reactant, it's not a product, but does help the reaction proceed and make it go a bit faster. But again, today we're going to focus on solid, liquid, gas, and aqueous. Every chemical is going to get this label. And so here's some chemicals here. Now, how do you know it's a liquid? Well, there's liquid mercury and there's liquid bromine. Those are your two liquid elements. But in terms of our ionic compounds, water, again, finds its way in. Water is not an ionic compound. It's actually quite covalent, but it can still fit in here, and water is liquid. And so that's the one liquid that we get to use. Is the aqueous and the solid that's going to take a bit more work. Aqueous and solid is going to be determined by a chart, a table like this, where you have multiple cations finding anions, and when the cation hits the anion and meets, you get to kind of read this chart and decide if it's aqueous or not. So it's just a couple of examples. Let's just look at this one here. So lithium is my cation, and fluoride is my anion. That's properly crisscrossed. And so what does that do for us? Well, that's aqueous. So AQ, aqueous. Let's come up with another one, just kind of circling. Let's try calcium and just try nitrates. So you kind of follow the table and see where they meet, and it's aqueous. So when calcium nitrate comes together, I'll crisscross it properly using our Unit 2 skills. That is aqueous as well. Let's try to track down a solid. So a solid can come from, let's try this one here. So that's the S for solid. So that's hydroxide and aluminum. So Al, I'll crisscross properly. And then you put a little solid out there. Aluminum hydroxide is a solid. So when that gets added to water, that's made in water, it's going to, the cation is going to find the anion, stick together, and stay stuck together and stay as a solid and not dissolve in water and be ripped apart ion by ion, or stay apart ion by ion. The cations will find the anions and it will stay together as a solid. And so another solid over here, let's see what this one is. So chromate and zinc. So ZnCrO4, that will be a solid. And so it takes practice to get to use this chart, and practice we will do. And so here's a chemical reaction with a couple of products for you. We're going to try to determine these states. So you're going to have to track down the cation and the anion on this table. And so we can do that. So here's copper here's copper and here's sulfide, and where they meet is right here as a solid. So this question mark is no question mark anymore because this table tells us it is a solid. And what about the sodium nitrate? Well, let's track it down on the table. Here's the sodium, here's the nitrates, and that's aqueous. So this question mark is a question mark no more. It is aqueous. So we've made a solid and we've made an aqueous compound. Let's try another one. Okay, so we have sodium and nitrate. Sodium and nitrate is aqueous. So let's change that question mark. And now let's try potassium and sulfates. So let's track them down. Here's the potassium. Here's the sulfate. They meet here, AQ. AQ means aqueous. And so that question mark is aqueous. Now, 2 aqueous is going to be something in a moment, but for now we just have 2 aqueous. 2 aqueous. Let's try another one. So here is barium and sulfate. So barium sulfate, that's a solid, and sodium sulfate. Here's sodium and here's sulfate. That should be a nitrate. I'm going to fix that, but not yet. It still works for us. Sodium sulfate is aqueous as well. Or not aqueous as well. Sodium sulfate is aqueous, barium sulfate is solid. And so the S for the solid, and there's the S there. So whatever you see on this table is the physical state you're going to write up here. What about this one? So we have aluminum nitrate. And so there's the aluminum, and here is the nitrate. So that's aqueous. That question mark is going to be aqueous. And then lithium acetate, it's one of the bigger polyatomics we have, CH3CO2. So here is the lithium, here is the acetate, and they meet as aqueous as well. Even the reactants, aluminum acetate, you can track down. There's the acetate, there's the aluminum, that was aqueous. Lithium nitrate, LiNO3, that's aqueous as well. So both of the reactants are aqueous and both of the products are aqueous. I mentioned there was a trick. When we come to both products being aqueous, so no solids, no liquids, no gases, just aqueous, we actually say there's no reaction because we're not going to have any indications of a chemical reaction. It's not going to form a color change. It's not going to form a new compound with a new physical state, with a new color. So we actually say there's no reaction. You have to have a solid or a liquid or a gas form for a reaction to take place. If everything is aqueous before and afterwards, we say there's no reaction. And so that's my slide there to put it to a bigger font for you. And so this is going to take some practice. You just kind of keep going on to this table and keep tracking things down. And so good luck with the worksheet. And please remember, chemistry is everywhere.